In this section, we're going to look at measurement uncertainty, and what that really means is to how many digits can you trust a measurement that you made. So what we have in the picture on the slide is a graduated cylinder, and we want to see the correct measurement to take from this graduated cylinder. First of all, you'll see from the graduated cylinder that the numbers are smaller at the bottom and get bigger towards the top. What we're going to read is where the meniscus sits. And you remember the meniscus is the curved surface of the liquid. Fortunately, there are some blow-ups here so that we can see more clearly where the bottom of the meniscus is. And that's where we're always going to make our reading. If we look at the numbers on the graduated cylinder, they go up by 5s. Each big division is 5. But between those, there are 5 little subdivisions, so each little tick mark counts as 1 milliliter. Therefore, I can see that this reading here is definitely somewhere between 21 milliliters and 22. So I'm going to write that we've got 21 and then some. Now, I won't be able to say for sure what the next digit is, but I'm going to mentally subdivide that gap between 21 and 22 into tenths and estimate the next digit. I think it's a little more than halfway up between the 21 and the 22. I'm going to estimate that that's 21.6, and we always put a unit, 21.6 milliliters. Now, I wasn't certain about that last digit. If you had said, and I hope you took a measurement before I did, if you had said it was 21.7, I would have believed that too. That digit is uncertain, but it's close enough to be worth something. So what we always record is all the certain digits plus the first uncertain digit. In general, we read to 1/10 of the smallest division. Because the smallest division I'm certain of, and the 1/10 of that is the first one I'm uncertain of. It makes no sense to record fewer decimal places. That's throwing information away. It's really crazy to include more decimal places that you would be completely making up. So there's a special term we have for the certain digits plus the first uncertain ones, and I suspect you've heard it in high school before. What I'm talking about are significant figures. Certain plus first uncertain digit. That term has a meaning. Significant figures truly are significant. They have meaning to them. So although you've probably learned some rules for significant figures, we're not going to memorize them. We're going to study them in enough depth to make them make sense. My toughest sell for this is to make people believe they truly are significant. But if you're the one in the lab earning the digits and you've got to pay more money for better equipment to get more digits, you will truly find them significant as well. So suppose I had a measurement that I reported as 50.0 milliliters. What that means is, having recorded it correctly, that the 50 are certain and the 0 after the decimal point is uncertain. In other words, the reading is between 49.9 milliliters and 50.1 milliliters. In other words, plus or minus 1 in the last digit. I would measure that probably with the graduated cylinder to get that number of digits. However, I could use a device called a burette, which could measure to 1/100th of a milliliter. If my reading were 50.00 milliliter, that means that the reading is between 49.99 milliliters and 50.01 milliliters, which is a much smaller range. I know that value with more precision than I did for the 50.0. What I concluded here is that we generally assume plus or minus 1 in last digit. That's generally. Sometimes you can't estimate it to that close, but I'll indicate those cases when we run across them. Another way I can express this difference in uncertainty is to say that 500.00 milliliters is a more precise measurement than 50.0. In other words, I know the 50.00 to more decimal places with less uncertainty in it. It's more precise. So, remembering that we can assume plus or minus 1 in the last digit and that significant figures are the certain digits plus the first uncertain one, finally it's time for you to give a chance to practice your understanding. For each one of these meters with the arrow on it, I'm going to have you decide what the proper measurement should be. If we were in class together, I'd pause and give you a chance to think about what it's going to be. I will try to pause briefly, but maybe you want to actually pause the video as we do it. So when we look at the first reading here, take a second, pause the video, and see what reading that arrow on the top indicates. What I see is it's somewhere between 20.123 and 20.4. So it's 20.3 something. We're going to estimate 1/10 of the smallest division. It looks like it's in between the two. I'm going to put 20.35. I estimated that. If you said 20.36 or 20.34, I would believe you. Plus or minus 1 in the last digit makes perfect sense. There's always uncertainty in the last significant figure. Now, normally I'd need to put a unit on this, but this scale has no unit, so it's appropriate for us to leave the units out this time. All right, looking at the next one, I'm going to pause. Maybe you want to pause the video and decide what measurement the arrow is indicating. I see it's between 20 and 21. That's what I'm certain of. I'm certain to the nearest one. But I'm going to estimate 1/10 the smallest division. The smallest division is 1 here, between 20 and 21, so I'm going to estimate the nearest 10th. And I'm going to say maybe that's 3. Although if you had said 20.2 or 20.4, I would have believed you as well. So again, we record it to 1/10 the smallest division. All right, moving over to this side, pause the video and make your reading. I think that's definitely between 108 and 109. So I'm certain it's at least 108. Now I'm going to estimate 1/10 of the smallest division. I'm going to estimate that that's 0.5. Although if you said 100.4 or 100.6, you'd be right as well. Okay, last example. Tell me what you get when you read that arrow. Pause the video just to figure it out. I'm sure that it's about 108. I'm certain of that. But because there's tick marks every one, I'm going to estimate it to the nearest tenth. Now, I think it's right on the tick mark. So I'm going to say 108.0. That's the correct number of significant figures. I couldn't just say 108 because that would tell me I knew it only to the nearest 1. It was somewhere between 107 and 109. But I'm much more sure of its precision than that. It's closest to the 0. Some people tend to throw zeros away, but really a 0 is no different from any other digit. I could measure a 0 at the end of my number just as well as I could measure a 5. When we're in the lab, we will use those understandings to make our measurements. Now the next thing we're going to do is count how many significant figures certain measured quantities have, and we're going to assume in each case that these have been recorded correctly. This is a kind of an academic exercise. The value will be when we start doing calculations with these numbers. We need to know how many significant figures are in the number to know how to carry those values through the calculation. Now, in high school, you probably memorized some rules for significant figures. We're not going to do that here. Memorizing is evil because to me, memorizing means you just pounded it into your head, not that it makes sense. We want it to make sense, and that way you don't have to memorize it at all. Remember, significant figures are measured figures, and that should cover every single case. While I'm at it, just let me point out that we will always make sure we have the correct number of significant figures in our results. I know you may have learned this at the beginning in high school and then your teacher never cared afterwards. I promise you I wouldn't teach you anything if it wasn't important for us to use it. Significant figures are not the most important thing that we're doing. It's the icing on the cake. But let's learn the conventions and get it mastered early so we never have to focus on it again. All right, so the question is, how many significant figures are in the following measurements? For A, I want you to look at that and decide how many significant figures while I pause. I see 4 significant figures there. Remember, the big picture is which one of those digits are measured. They all are. Why would you have written that digit there if you hadn't measured it that way? Based on that understanding, which I hope is kind of intuitive, the rule comes as an afterthought. Non-zero digits are significant. That's our conclusion based on our understanding. That's not our starting point. That's not something to be memorized. All right, let's go on to B. I'm going to pause and you're going to figure out how many significant figures are in that number. Remember, that means how many digits were measured. I see 2 significant figures there. The 1 and the 2. Those zeros at the beginning are only placeholders. A way I can illustrate that is to say that although it's 0.0012 liters, I could also express that as 1.2 milliliters. And in 1.2 milliliters, there are only 2 measured values. So the zeros at the front are only placeholders. They don't count. Leading zeros are never significant. They're just placeholders. Okay, on to the next example. In C, I have 4 different representations of a number that's all the same magnitude. We're going to tackle them one at a time and see which digits are measured. That's how we know how many digits are significant. So I'm going to pause and let you think about the first number. I think that that has 7 sig figs because I think that 0 is significant. Why would somebody have put that 0 there if it wasn't? So I can see that all the digits are significant. 1, 2, 3, 4, 5, 6, 7. What that means in terms of the precision of the number is that I know that measurement to the nearest 1/10 of a centimeter. I can trust it to a 1/10 of a centimeter. All right, on to the next one. I'm going to pause while you decide how many significant figures are in it. This situation is the situation where you get the greatest ambiguity. The convention that I follow is that it's only to the nearest 100 and that those trailing zeros are not significant. I'm going to contrast it with the next number that actually has a decimal point here. And the way we're going to indicate the difference between these is we're going to say that trailing zeros, zeros at the end of the number, are significant if and only if there's a decimal point in the number. Trailing zeros are significant only if there is a decimal point. That's going to let me express different levels of precision. The second number here that doesn't have a decimal place has 4 significant figures. The trailing zeros don't count. And what that's telling me about the measurement is that I can trust it to the nearest 100 centimeters. But the number after it with the decimal point, because there's a decimal point, all of the zeros in the number are significant. So I see 6 sig figs there. And in practice, what does that mean? Remember, significant figures are all the certain ones plus the first uncertain one. In other words, I'm uncertain in the ones place. I know that measurement to the nearest 1. So I've shown you a way to express that measurement to the nearest 100 and to the nearest 1. How would we express it to the nearest 10? How would we express it, in other words, to 5 significant figures? The best way to do this with no ambiguity is to express it in scientific notation, because by definition, scientific notation has a decimal point after the first number. So because there's a decimal point there, you can see that there are 1, 2, 3, 4, 5 significant figures. Trailing zeros are significant if and only if there is a decimal point. The next example shows a number that I am absolutely certain of. This is a counting number. And this example comes from the good old days when a group of you would be sitting in a classroom in front of me. I could count the number of students in the front row with absolutely no uncertainty. Significant figures are meant to show how much uncertainty you have in the number. So if you have no uncertainty, you have infinite significant figures. Exact numbers have infinite sig figs. More meaningfully, that means it has 0 uncertainty. So if I were in a classroom with you all in front of me, I could count with no uncertainty the number of students in the front row. But if I wanted to estimate the total number in the classroom, I would probably be uncertain that I had that to the nearest one, since there would be about 60 of you probably. Counting numbers are exact, and another kind of exact number is a conversion factor. By definition, a 1,000 grams converts to 1 kilogram. Exactly, by definition. So again, there's no uncertainty that those numbers have infinite significant figures. When you get your assignment for this week, you're going to get lots of chance to practice this skill. And I hope if you have questions about what I've just shown you, that you'll bring it up in tutorial as well. Let's pause for now and continue section 1.5 in another video.